Welcome to Manish Kumar channel. So today we are going to discuss about ordered basis, right, and coordinatization. So this is very useful topic because it will be used further when we are talking about matrix of linear transformation, right? So this is a foundation basically. This lecture is going to help you to identify when we are talking about the matrix of linear transformation. This is a base for that for upcoming videos. Okay, so now if we talk about the definition, so an ordered basis for a given vector v is an ordered n tuples of the given vectors v1, v2, vn such that this set will be a basis for v, right? So here order matters. So v1, v2, vn, right? If we change the order, then this becomes another ordered basis. You got it? So now this is a very, very important concept while defining the ordered basis. Here, every vector like v1 first place and so on, the vn is the last place will be an ordered basis. So here we are not going to change the order of the given vectors. Okay, and this set forms a basis for v. So the definition, script b is an ordered basis for a given vector space v. So it means that any W can be written as the linear combination of the basis vector because of the fact that B is a basis, right? So basis properties means basis can span V. So any element of V can be written as the linear combination of the basis vector, right? And how do we represent this coordinatization of W with respect to B? We write it as W given with respect to the given basis B, right? Alpha 1, alpha 2, and alpha n. Okay. So the method of coordinatization. So the method of coordinatization is very simple and has few steps, right? And very important also. So suppose V is a non-trivial subspace of Rn and B is an ordered basis, let's say V1, V2, Vk, be an ordered basis for V, then let any V belongs to Rn. To calculate V given B, if possible, we perform the following steps. So what I am going to do here is I'll write A augmented B given V with the help of vectors in B as a column of A. So we are basically preparing the every vector we are going to put as column wise, right, to get my A matrix. So A matrix is going to be like V1 transpose. Column matrix means transpose of this vector. V2 transpose, right? So like that we are going to assign and so on. Vk transpose. Okay. So this is my A matrix, and to which we want to see whether this vector belongs to this coordinatization or not, whether this vector can be written as the B basis coordinatization. We write as the next column, right? A augmented this given V, right? So this is how we prepare. Is a similar way of solving AX equal to B. So B will play a role of V, right? And A is the column of given basis V. And we are solving such system, right? And you know how to solve such system because many problem we have done. This is a non-homogeneous system of equation you are going to solve, whether such system has solution or not. If the system has solution, then means every V can be expressed as the given basis, right? If not, then coordinatization of that V is not possible. Okay, so if you see, the method is very simple. Form an augmented matrix A given V, where A is the column of the basis vectors, and apply RREF, reduced row echelon form. I refer to watch my second video where the RREF has been explained. And if there is a row of this augmented matrix CW that contains all zeros on the left and has non-zero entry on the right. Left and right means this is left. This entire part is left and this is right side, right? So it will be a form like you have no solution, right? Then V does not belongs to span of given basis B. It means that coordinatization is not possible. Okay, then we can stop. Otherwise, V belongs to span of given basis B. It means eliminate all rows consisting entirely zeros in given C augmented W and obtain a matrix of form IK then B the basis B for the given vector coordinatization is going to be as Y element, right? That is the last column of your augmented matrix. Okay, so we can see this with an example. So let V be a subspace of R3 spanned by the ordered basis. So ordered basis, two elements are given. So two elements cannot span entire R3. So it will span subspace, right? So this is a basis for the subspace. Now we want to know, use the coordinatization method to find V given B, where V equal to 10, minus 12 and 20. So is that possible to write the coordinatization of this V given this basis? So what we have to perform? We have to write this as the transpose and put into the column wise. So if you see the augmented matrix, transpose of first column with the V1 transpose, second column is the second basis transpose, and right hand side will be the given V which you want to know, and apply RREF on the above matrix. What we will get? We'll get this, right? So this means this is the form actually, right? So what is this vector? This vector is your right hand side. We are going to plug out and call it as Y, and this is IK type, I2 type, 2 by 2 matrix, right? So ignoring the last row zeros, we find the coordinatization is possible because the system has solution, right? And then V can be written as given basis minus 4 comma minus 1. So this coordination is possible. So let me just understand what we are basically doing in coordinatization. So with a very simple example, I'm going to explain. If you think of like R2, right? So I want to represent this vector, let's say you can say that V, okay? And since R2 has basis, let's say I can say 1 comma 0 and this is 0 comma 1, right? So basis, one basis is ordered basis, if I say is consisting of 1 comma 0 and 0 comma 1, okay? Another ordered basis I can say with this, if I do change the color, then you will get to know. Another basis is, let's say, this and this. Okay, so what is the basis now? B1, I can say ordered basis. So first vector will be 0, 1, and then second vector will be your here minus 1 comma 0. So this is another basis for R2. This is R2 if I'm talking about, right? R2 means plane. Okay. So now the question is, any vector V, any vector V can be written as the linear combination of, you know, alpha 1, 0 comma 1 plus alpha 2 minus 1 comma 0, right? And we solve for alpha 1, alpha 2. Similarly, I can also think of this V, the same V can be written as beta 1, 1 comma 0 plus beta 2 0 comma 1. So the basic idea is the same vector v I want to represent with two different bases, right? That means with this basis I want to represent the u with this given v, and with this basis green one I want to represent the given vector v. Since basis is not unique, so we are going to find the coordinatization of v with respect to different bases. Okay, this is the idea. We are transforming, we are going to learn about the transformation. If you see previous basis vector is like this 90-degree angle, right? Now we are rotating it basically. If you rotate this, you will come up, this vector will come up, this vector will come up to this position, and this basis vector will come to this. Means it is a 90-degree rotation basically of the plane, right? And now we want to represent the same vector with this basis. So this is a kind of transformation we are going to learn later. Matrix of transformation, this is heavily used. So this is how the motivation for learning matrix of transformation, which will be a linear transform, we will see in few videos later. Okay, similarly, if you see I want to apply on this vector, does this vector belongs to this given span, or in other word, does this vector, can we write this vector v as the given basis coordinate? It means coordination is possible or not. So we do the same, we allot this v as a right hand side and as basis in the column wise, and then solve RREF as usual method what we did. So we got this scenario. So if you see here, we got this scenario. So what had happened? The rank of A matrix, right, and rank of augmented matrix. Rank of A is how much? 2. Rank of augmented matrix is 3, right? It means that system has no solution, right? Inconsistent solution. Okay. So therefore, coordination is not possible. Okay. Then now, what is the result? If B is an ordered basis V1, V2, Vn, right? And suppose W1 and W2, W3 and so on, Wk belongs to V, and scalars alpha 1, alpha 2, alpha k are real, coming from real field, then W1 plus W2 ordered basis given with respect to coordination with respect to B is same as the individual sum. Alpha times of W1, right, coordination with respect to B is equal to alpha times the coordination of W1. And this will be true for the linear combination as well, right? Now the idea comes into the mind, okay, do we have any method like every time if you give me the basis vector, I can write augmented matrix A and then solve for right hand side every time? Do I need to do RREF again and again, again and again? Then you can always find the right hand side vector B using the transition matrix. So transition matrix will always give you every vector has a solution, right? So you need not to solve RREF again and again once you have that transition matrix in your hand. Okay, so this is how transition matrix works. So suppose V is a non-trivial vector space, right? With respect to two bases, two ordered bases B and C, P be the n cross n matrix whose ith columns I equal to 1 to n equals B1, B1, B2 and so on with respect to C, where Bi is the ith columns of ith basis vector in B, right? Then P is called the transition matrix from B to C, right? So what does it mean? How do we calculate? What is the method for calculating it? So if you see P is a transition matrix from B to C, so first write the C vectors column wise and write the B vector column wise, and form an augmented matrix like this: A type of B, both are matrix. Rather than going to one column vector right hand side, we are replacing one column vector by the matrix. Okay, so once we have the matrix, I can easily get it multiply for a given vector to make sure that it is going to be coordination is possible, right? Okay, so now you can write the first column, first vector in C, second vectors in C, and so on, third vector in C. Similarly, B vectors you allot as column wise, and then apply RREF. After applying RREF, you will reduce to this form, right? I zeros as we have seen before one case, right? And P will be the transition matrix, right? So now if you see, suppose B and C are ordered basis for a non-trivial n-dimensional vector space V, and P be an n cross n matrix, then P is transition matrix from B to C if and only if for every vector V, we can always find the coordinatization, right? P given vector V can be written as the coordinatization in terms of B is same as we are going to multiply with the transition matrix to reach to the uh, B with respect to the new basis vector C. Okay, so if you see like this is a vector space V and this is vector space V having two bases B and having two bases, you can say C. Okay, then we are transforming any vector with respect to P. P is the matrix of transformation, right? And any vector V can be written as the linear combination of the basis vector V. So that means coordinatization with respect to B. And if we multiply P, then I will reach to here, and any vector V can also be written as the coordinatization vector of C, right? Then we will reach as V with respect to coordination of C. So in this case, coordinatization is always possible if we have the transition matrix, right? So this is how we are going to work. Now another theorem, if B and C are ordered basis from a non-trivial n-dimensional vector space V or finite dimensional vector space V, P be the transition matrix from B to C, right? And then P will be always non-singular. If P is non-singular, then inverse always exists. Non-singular, I mean determinant of P is non-zero, right? Determinant of P is not zero. Okay, so P inverse always exists. So this will be back actually. If you look at in this picture, determinant of P is non-zero, then inverse always exists, and which is nothing but P inverse, right? And that will be the coordinatization from C to B. How we find from B to C, if and P is always invertible, so we can come back from C to B also, right? So this is called inverse transformation, right? And the last one here, if you see, B, C, and D are ordered basis for a non-trivial vector space, right? Finite dimensional, and P with a transition matrix from B to C. So if you see this result, I can say here B B coordinates means basis of B, and suppose if you have C coordinates and if you have D coordinates, right? So from B to C you have a matrix P, right? And from C to D, this is the theorem says, right? C to D you have a matrix of transition matrix Q. And since we know transition matrix, if I want to know from B to direct D, right? So what I will do, QP will be the transition matrix. I do multiply Q, then P, I will reach directly from C to D. This is what this theorem says. So P be the transition matrix from B to C, and Q be the transition matrix from C to D, then QP will be the transition matrix from B to D directly, right? On the other hand, if you see, since we know P is a transition matrix from B to C, then we can always find transition matrix P inverse because of P is non-singular, right? And from C to D, if you reach, it will go from D to C, it will be Q inverse, right? And I can also go back from D to B using this, what I can say, QP inverse, right? QP inverse. You see, QP is a transition matrix from B to D. So QP inverse will be the transition matrix from D to B. Or else you can follow the method P inverse Q inverse, because if PQ are not abelian, not commutative, then we can find P inverse Q inverse. P inverse Q inverse will be the transition matrix from D to C. So this is the structure of your finding the transition matrix. So they will ask some question, B, C, D are given, find the transition matrix from B to C, then C to D, and then what about B to D, or in other word, what about the transition matrix from D to B or D to C, and so on. So since you know how to calculate the transition matrix, you have to allocate the matrix as B to D if you want to write. So you have to have like this augmented matrix. Suppose P is a transition matrix from B to C. So you have to allocate the column with respect to C1, C2, and so on. And then here B1 and so on, B, K, whatever it may be, whatever the dimension and all, right? Then means I want to say here B to C means write C column vector and then B column vector right hand side, apply RREF, and then you will have a matrix like this, right? So here you will get I and here you will get P, right? So this is how the transition matrix work, and transition matrix will be non-singular, so P inverse also exists. Okay. So let us do one problem. Consider the ordered basis B, C, and D. Okay, then if you see here, none of them are standard basis, right? Say 1, 0, 0, 0, 1, 0, 0, 0, 1. So standard basis, you can directly calculate the transition matrix with respect to the given basis B. But here all of them are non-standard basis. So problem becomes little tricky, little difficult. Okay. So what is the first question? Find the transition matrix P from B to C. From B to C, if you want to do first part, so you write C transpose, 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 and allocate into the column, right? All transpose you can allocate into the column, okay? And then form augmented matrix with respect to B, transpose, 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 I mean row becomes column actually, right? So now if you find B and C, so to do for first, so you can write the C and then B, B, and apply RREF. Then this is similar to the given matrix. So this becomes the shape of identity and this becomes P. So you take out this matrix outside and write P can be the same matrix. Your answer will be this matrix 1, 0, 1, 1, 8, 0, 0, -1, 0, right? Once you have this matrix, you can use the previous theorem and then transform any vector V in given basis B and then multiply, you can get it into the C, right? So you need not to solve again and again RREF. This is the advantage of getting, transition matrix. And once the transition matrix exists, every vector can be written as the linear combination. That means coordinatization is possible. Okay. And now for part B, we have to write D first and then C, because C to D we are going, and then write the basis element as a column vector and then solve using RREF. So this matrix is going to be similar as this. So now Q is this matrix. You can take out the element. Q will be -1, 0, -2, 1, 1, 10, and then 0, -1, -9. So this Q is. So what is the part A and B? If you see, part A and B was find the transition matrix P from B to C, find the transition matrix Q from C to D. If you look at this picture, uh, B to C, we have obtained P, C to D, we have obtained Q, right? And what is the part C? Part C says that verify the transition matrix R from B to D as equal to QP. So what you have to do, first you write the from B to D we want to go. So first we write the D vectors as column and then write B vector in the right columns and then perform RREF to get the matrix QP, or else we have already have in our hand Q and P. We do get multiply these two matrix is nothing but the new matrix from B to D. So this is what in this problem they are saying, that verify the transition matrix. So they're representing D to B as R. So what exactly here R will looks like? R is nothing but this, R equal to QP. So they are saying that R is a transition matrix from B to D. Then verify this statement. R is nothing but the product of QP. So we will verify in this problem. Okay. So now what we have to do, first we have to write the transition matrix. So D to B, so we will allocate D column vectors and B here, and then apply RREF, which is similar to this matrix, right? So this is your R matrix basically first, right? R matrix. R matrix is going to be -1, 2, -1, 2, -2, 1, and -1, 1, 0. So once the R matrix is in our hand, uh, we do the method, because they want you to verify. Verify means verify this transition matrix is equal to the product of Q and P. Q and P already you have obtained. Just do multiply and check whether this is equal or not. Okay. So we have this, R. Now if you multiply these two matrices, P and Q, you will get the R. This is just verification. R is equal to Q and P, right? So this you have to do. I can show you in this. If you see Q and P, Q is this and P is this, right? Then QP is going to be this matrix, which is exactly your R. If you see here, R is -1, 2, -1. So first row will be -1, 2, -1. So this is just verification has been done in this part, but you have to do it as a separate part, right? This is an exercise for you. Okay. And what is the last part? Last part, they are saying that use the answer to part C to find the transition matrix from D to B. D to B we have to go. D to B means you see here from this picture, D to B. D to B means this is basically R inverse, right? R inverse is nothing but R is equal to QP. So QP inverse. QP inverse is P inverse Q inverse. Already you have QP in your hand, which is R. So you can just use the formula for getting inverse, and your part will be done. So now use part C. Part C means QP already you have calculated, or R you have already calculated. to find the transition matrix from D to B. So inverse they are basically asking. So the last part, so finally to find the transition matrix from D to B, compute R inverse. R inverse is QP inverse, P inverse Q inverse. So Q is this, P is this, whole inverse is nothing but QP. This is QP basically, and that is nothing but, if you see in this Q inverse and this is P inverse and Q inverse, like that you can find, and that is same as R inverse, right? So this is all, your problem is done. Another important result using the transition matrix, we can always diagonalize the given matrix A into the diagonal matrix D with the help of transition matrix P and their inverse. Since diagonalization is possible for such a matrix, right? So when the diagonalization method is applied to a matrix to create a diagonal matrix D, which is given by D equal to P inverse AP, as P is non-singular, so P inverse exists, and a basis of fundamental eigenvectors, then the matrix P is in fact the transition matrix from B coordinates to the standard coordinates, right? So this is another result, and diagonalization is very useful in many fields. Okay, so thank you. Thanks a lot.